You start from counting things, and in the end, you apply the condition of equilibrium and you arrive at thermodynamics.
Any system, once again, any system thakile, let's say the volume ase V, tar bhitorot there are n number of particles, gas particles, and there is a total, so total energy is some E. V is the volume, N is the number of particles. Now, that can be achieved in many ways. These n number of particles can be distributed like this. This one we can say, still NVE. So this, as long as this is NV and E, that's one macrostate. Corresponding to that, the gas particles can be here, and that will say, let's say, one microstate. We can also have like some of these particles on this corner and this particle in this corner, right? And the velocities are slightly different, but still total it's NVE again. So let's say that's microstate 2, and so on. We can go on, slightly changing another, slightly changing another. These are all microstates. And this total number together, so the last one, let's say last one, is called omega NVE. This is the total number of microstates. So in case of a dice, if I say any outcome, 3, 4, 5, 6, 1, যেকোনো কে আহিলেও, we are fine as long as there is a throw. Then this throw is called a macrostate, any, and the number of microstates are 6. Another concept we need, studied in one of the classes, is equilibrium. The concept of equilibrium. What do we mean by equilibrium? One, it should not be changing with time, so it should be stable. So which means it should be always, or most of the time, found in this particular state. So most probable state. What that means, just with an example, is that if you had a box and you had some gas particle inside, and this is a state, and there was another state. So this has some n number of particles, V is the volume, total energy E. But this also satisfies that. This still has n number of particles, V volume, and total energy is E. But here, all the gas particles are on the left half of the box. Okay? Now this state is not really equilibrium. We know that. Soon they will start diffusing. So most of the time, you will find, after some time, let's say you started with this, and after some time you will find it in this state. And then it will stay in this state. But that does not mean that all the particles are fixed, right? They're constantly moving, but it will look the same. So this is more like equilibrium. This is not. What is this definition in terms of our counting? Omega NVE. That this should be maximum. Why this should be maximum? Because consider this one. This has a probability of finding this. I explained this in another class, so I'm not going to calculate. Probability for this is 2 to the power minus n if there are a number of particles. The probability of this in compared to that is 2 to the power or 1, let's say. So this, if you take really huge number of particles, 1 mole, let's say, 10 to the power 23. So this will become 2 to the power 1, 23 zeros. So that's really almost zero probability. So you will almost never find the state
the box in this situation. Any of these state, this, and let's say this, so they all have various probabilities. But if you counted like every microstate, for example, throwing a dice, you throw a dice, probability of finding 1 is 1/6, probability of finding 6 is also 1/6. So these all microstates have the same probability. But if I give you 2 macrostates, where in one case I ask, what is the probability that either 2 or 3 will come? Okay, so that's what, 2 times 1/6, 1/3. And then I ask, what is another microstate? Another microstate I say, I'm happy if either 1 or 4 or 6 comes. So what is the probability of that macrostate? 3/6, that is half. So that is more probable, right? More probable is connected to how many macrostates available. If there are more macrostates, that is more probable. But individually, each macrostate has the same probability. It's counting, so you really constantly need to practice these things. This whole subject is counting. So, the macrostate that has maximum number of microstates is the most probable one. And if something is most probable, obviously, the system will move towards that to find the maximally. What does that mean? Most of the time you will find it in this state. That means this thing, first we need to calculate for a system and then take a derivative and put that equal to 0. Variation of something equal to 0 means gives you the maximum value, the condition of maximum value. So if you, for example, if you varied it with delta E and put equal to 0, so at certain value of E equal to E max, let's say EM, this will be maximized, and at that value, the system will attain equilibrium. So now I will apply this to a system and derive a very important formula in statistical mechanics and thermodynamics. Consider 2 boxes, initially separated. This has N1 number of particles, its volume is V1 and its energy is E1. This has N2, V2, E2. Okay, they are separately in equilibrium. No energy can escape, nothing can escape. So fixed. Considering this, it has, let's say, omega 1 N1 V1 E1. That's, let's say, its total number of microstates. So this is a macrostate I gave you. There will be some number of microstates, right? This will have again its own it will have its own number of microstates. And we know that these are like probability. These are like probability. In case of dice, 3 faces when we had more probability, 2 faces, less probability. So these are like probability. If they are like probability and these 2 systems are separate and independent, like 2 coins, then their combined probability of finding any one of them in any of the states is just a multiplication of the 2. So that the combined number of macrostates will be, I'll put the function here, omega 1 N1, let's just write, let's denote by just energy. Because anyway, others are constants. Even energy is constant. But for now, let me just put the energy here. We understand that there are N1, V1 are there. Okay. This is it. Fine. This is the total number of microstate corresponding to this combined system. Now I bring them in contact. Okay. Now I bring them in contact. There is a wall between them, so particles cannot mix. Volume obviously is going to be the same, but heat can be exchanged. So energy can flow between the two systems. Remember, they were separately in equilibrium. So you can imagine these two as some cylinders of gas with, let's say, flux. So individually heat cannot flow out, but then you bring them in touch and replace with a thin metallic wall that energy can now flow. Okay. Now the question is, energy is flowing fine. At what value of energies the combined system will attain an equilibrium? Obviously, when you bring them together, it's not equilibrium, because you will see maybe now the energy is some E1 bar, let's say, not bar, let's say E1 prime, E2 prime, then it's constantly flowing. After some time, energy change hui jabo, this whole, they will keep flowing. Higher energy to the lower energy, it will keep flowing. And because the system is continuously changing, it's not equilibrium. But at some point, we know that when the temperature becomes equal, they will be in equilibrium, right? This thermodynamics from your third semester. We are asking, let's say at certain value of E1 bar and value of E2 bar, there will be an equilibrium. What is that value, or what is that condition on these values? Okay, that is the question. And the condition, we have some conditions. So E0 equal to E1 plus E2. Total energy remains fixed. This is simple energy conservation. Right? Energy can flow, but as a whole, it remains the same. That's the only condition. Okay, we can write then E2 equal to E0 minus E1. Now let's exploit this formula. That means I can write this thing as E0 minus E1. Right? I can write this. Which means this side you see only E1 and E0 is there. So I can write this as a function of, you can write it here as E0 and E1. Yeah. This combined function. Now remember, this function is now changing because now the two things are in contact. So we have omega 0, E0, E1. And that is simply this. Let me again write it as omega E1, omega E2. Obviously E2 equal to E0 minus E1. That's what I mean. I just wrote it like that first to show that only E0 and E1, E1 and E2, or E0 and E1, similar variables. So I just replaced this E0 by this. So this one was E1 and E2 actually. The combined one is a function of E1 and E2. Was not E0. E1 and E2. So E1 and E2 will keep changing due to energy exchange. Now let's apply the condition of equilibrium. And what is that? E0 is a constant. So E1 is a variable that's changing. We can take either E2 or E1 as our variable because it's the same thing. They are connected by this. So let's take E1 as our variable. We can say del omega 0 E0 E1 del E1 equal to 0 at certain value of E1. This is the condition of maximizing this number of microstate function. This will give us the condition for equilibrium. Okay.
What do we get when we do the derivative on this side? We get del omega 1 E1, del E1 at E1 equal to E1 of course bar times omega 2 E2 plus omega 1 E1 del omega 2 E2 by del E1, right? By del E1, because that's what we are using. But that we can write E2 del E2 by del E1. Chain rule at E1 equal to E1 bar equal to 0. Now what is del E2 by del E1? It's minus 1. If you calculate del E2 by del E1, minus 1 count. E0 is constant. So if you do dE0 equal to 0 equal to dE1 plus dE2. So basically del E2 by del E1 is minus 1. So this becomes minus, okay, equal to 0. So this becomes 2 equal to E2 bar equal to 0. So that means this equal to this. Or we can take this on this side here, omega 1 E1, and this on that side, 1 over omega 2 E2. So that means we have some 1 over omega 1 E1 del omega 1 E1 by del E1, 1 over omega 2 E2 del omega 2 E2 by del E2. This just means del E1 of log of omega 1 E1 equal to del E2 of log omega 2 E2. Which means this quantity is some constant. What quantity? If there was a quantity like this, del E ln of omega of E, then that quantity is constant, right? This thing of E1, this thing of 1 equal to this thing of 2, so it's constant. Now what is that constant? This means we found that equilibrium happens when this quantity, whatever it is, we don't know, becomes a constant. Now we know about something that it becomes constant when there is equilibrium. So what does this mean? If this we can name beta 1, this we can name beta 2 equal to some beta, and that's when equilibrium happens. Tell me from thermodynamics, what is that thermodynamic quantity that satisfies this at equilibrium? That some beta 1 equal to some beta 2 equal to beta, it becomes equal for the both system and the equilibrium is attained when there is an energy flow. Duta system ase, heat flow hoye ase. Ki bostu? Temperature. Yes. So temperature or logot relation to eta ase. It could be T, it could be 1 over T, it could be T square, right? Any function of T. If T becomes constant, any function of T will be constant. So this beta or this thing is related to temperature. This is very important that you understand. There is a system NVE. Correspondingly, there are some microstates. Count korisu 1, 2, 3 up to this omega. And tar hey counting to me maximize korisu. At equilibrium, that counting must be maximum. And we found a condition. So from counting to thermodynamics, we are trying to connect. So that's what statistical mechanics is really. You start from counting things, and in the end, you apply the condition of equilibrium and you arrive at thermodynamics. That's the aim. Okay. So microscopic things, counting to macroscopic things like temperature, volume, pressure, on those things. We know a condition like this from thermodynamics, if you remember. 1 over T. So if we divided this by that, then we get del S over del ln omega equal to 1 over beta T. Right? If we compare these two, then this is what we get. This can be integrated. So this is obviously constant. This can be integrated, and what we will get is some S equal to this 1 over beta T, and then ln omega plus whatever some constant S naught. Planck wrote it without the S naught. Just directly this. And this is very true and it's very famous. So 1 over beta T is called Boltzmann's constant. S equal to kb ln omega. On this side of the equation, left hand side, you have thermodynamics, entropy. On that side, you have counting of how many states. It could be dice or whatever. So you see, I mean, even a system of dice can have a concept of entropy. It does not matter like gas or anything. It could be market, like let's say in how many ways you can sell your share and get a profit or whatever. So those final profit will be your macro state, and how many ways you can sell will be the number of microstates. That will be omega. And even in that market system, finance, you can find a concept of entropy. You can define an entropy like this. People define entropy for black holes, of the universe, of anything really. Anything. Take a system of bacteria, and you can still define an entropy. Okay, so that's why, I mean, on this side, you can define entropy, and if you have entropy, you can get the whole thermodynamics from it. And this is really very intuitive. Just look at this. This is the probability. So when this number is very large, we know that the system will tend to go there. In the first class, maybe I explained something. Like you enter a library and it's perfectly organized, okay, everything in place nicely. And then somebody throws a book in the middle. If you come next time, you will know that no, it's not the same library, it's not the same state. So it's not the same macro state. That means this organized library has really less number of microstates. You make a little change and you know this is a different microstate. Now I really throw all the books everywhere. It's a completely chaotic, disorganized library. Now if somebody comes and changes a little bit the books, this book there, you will not understand the difference, right? So this disorganized library, that macrostate has more microstates, okay? And that's why if you leave the library like this organized and you come back after 10 years, it will be more disorganized because the library will tend to be in most probable state. Now the most probable state is where there are more number of ways you can get the same disorganized state than compared to organized. So if you organize it now, it has very less number of microstates compared to disorganized, where it has more number of ways you can change and it will be the same disorganized. So that's why with time everything gets disorganized. It applies to everything. It applies to relationships, where if you don't put your effort, so you have to put your effort really to keep things in place. Otherwise there will be breakups. So you know, things will tend towards more disorganized because that is more probable. A family, You have to, like, you can't have a family and never call them. So, I mean, you can keep the library organized, but you need external effort. Without effort, it will always tend toward more disorganized state. That's what is going on with the universe. Universe is moving towards more and more most probable state, the probability higher. And here we see that this probability is connected with entropy. So what we can say is disorganized means more probable state, more number of microstates. And that is related to entropy. So we can say that a system that has more entropy is more probable. So the universe will move towards, less probability towards more probabilities, less entropy towards more entropy. So naturally, entropy will always keep increasing. So that's why they say, like, entropy of the universe is always increasing. And that is your second law of thermodynamics. Comes only from counting and probability. Okay? This is very important. It's engraved in the grave of Boltzmann. So let's say we have some boxes like this, compartments. 1 box, 2 box, 3 box, dot, 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 ith box, and then some k minus 1th block. So 1, 2, 3, and then kth box. So we have k number of boxes. First, second, third, k minus 1k. K boxes. And I gave you n number of particles. And I told you that first box can have n1 number of particles. Next one can have n2. Third box can have n3 number of particles. Ith box can have ni number of particles. And this one, nk minus 1, kth box can have nk. You can think of these as balls, n number of balls you have to put in those boxes. The condition is that out of these n1 number should be here. So that could be 4, 5, I don't know. In general, n1. And that can vary. Okay. So, first, how many ways? So we have to do this. We are just given n. And initially these boxes are empty. We have to fill them. How? We have to put n1 balls here, n2 balls here, like that. Okay. So first let me fill the first box. We initially have n number of balls or particles. n1 I'm taking from this and I have to put it in this box. That is just a problem of combinatorics, NC-N1. For the second box though, you already have taken n1. So your available is now n minus n1. Not n1 anymore. Out of this, you have to put n2 in the next box. The third one, now you have taken also n2. So n minus n1 minus n2, these many available now. Cn3. And so on till k minus 1th. So how many really do you have here? How many particles? N minus 1 and 2. Just k1 or agar 2 kiman asil? K minus 2. So n minus, starting from n1 minus n2 minus blah blah blah, t minus nk minus 2. Right? Up to this much you have taken. C kiman? nk minus 1. That many you have to really put. And then the last one is easy. N minus n1 minus n2 minus blah blah blah. Nk minus 1. And the last piece, nk. And that will be your total number of ways you can fill these boxes. So NCN1 is what? N factorial by N1 factorial, N minus N1 factorial. This is N minus N1 factorial by N2 factorial, N minus N1 minus N2 factorial. Dot. This thing n minus n1 minus n2 minus dot 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 nk minus 2 factorial by nk minus
1 factorial, and then this minus this, so n minus n1 minus n2 minus nk minus 2 minus nk1 factorial, and the last one n minus n1 minus n2 minus dot 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 nk minus 1 factorial divided by nk factorial, and then everything will be minus now, n1 minus n2 dot 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 nk minus 1 minus nk factorial. You see that this gets cancelled with this next door logo. This will get cancelled with the next term here, and this will get cancelled with the previous one here, and this gets cancelled with this one here. And what is this? N minus n1 minus n2 minus all nk. If you sum the n1 plus n2 plus n3 up to nk, that's n really, because that's the total number you have, right? Sum of ni from 1 to k is nothing but your all the particles. So that is n minus n is 0, 0 factorial is 1. So basically you have a really simple formula. N factorial by n1 factorial into 1 divided by n2 factorial into 1 divided by n3 factorial dot 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 1 divided by nk minus 1 factorial into 1 divided by nk factorial. This is of course nothing but n factorial times, we can write it as product of 1 over ni factorial, I equal to 1 to k. This will be the number of ways you can fill those boxes. Okay. Now one level of complexity I'll introduce here, that's why I kept this formula. Let's take now one of those boxes, ith box, okay, ith box. Initially I had just one box, empty box. Now let's say the boxes can have some cells or compartments, but all of them are like let's say equal in some sense. So if you're, let's say, this box, if you are in this box, then you will have energy EI, okay? So if you were in this box, if a ball was inside this box, then that ball will have an energy EI. If a box is inside, let's say, second box, then that will have an energy E2, okay? But within that box, wherever they are, they will have the same energy. So what that means is, so how many balls go into this box? An I number, right? To the ith box. You can put all these Ni in the first one. That will be okay. How much will be the energy? Ni times energy of each ball, which is Ei, right? Or I could just take, these half of them in the first one and half of them in the last one. But it's, still EI and UI, and you plus them, and it's still NI, UI. So what that really means is, I gave you NI to go in the ith box. Take one of them, and you can put them in any of these. And there are GI number of them. So ith box has GI number of these cells. So out of Ni, you can take one of them and they can go in any of the GI. So how many ways they can go? GI ways. The second one you take, and again the GI are available because you can put in the same box. So even for the second particle, you can put any of those GI. So the second one, so let's say out of this Ni, first particle has GI ways to be filled, second particle GI ways, likewise ith particle GI ways.
So the total number of ways is just the product of them, which is how many ways? Gi to the power ni. Right? So that means here, if each box has their own cells, then the first box has G1 number of cells, second box has G2 number of cells, then each such boxes will have just this factor. So here G1 to the power N1, here G2 to the power N2, G3 to the power N3, Gk minus 1 to the power Nk minus 1, and Gk to the power Nk. So our final answer is Gi to the power Ni. We call the number of ways, we just denote this by, always by this, okay? You have n balls to be organized in k number of cells. We denote that by this omega, let's say just omega. And that omega is given by n factorial, product of I equal to 1 to k, Gi to the power k, Ni factorial. If you do not understand, try to derive it yourself, really. Take some boxes, maybe take 3 boxes and take 5 balls and do this exercise. That's really how we calculate the number of microstates. So in case of a gas, those balls are your particles and those boxes are really allowed energies. So when I say first box, so n1 number of particles goes to n this first box that has an energy E1. So that's what I mean. It is like pasta particle energy hobo, let's say 5 electron volt. Let's say 6 particles will have energy some 4 electron volt. So it is like exactly those energy values are like your boxes, and number is of course number of gas particles. So the same problem. So in a system what we will have, there, if it is a quantum system, it's easy to understand. Quantum system always have some levels, right? Energy levels. Particle in a box, for example. Particle in a box, they have levels of energy like this. So some 1th level, 2nd level, 3rd level, 4th level. You can think of them as boxes. And there could be 4 particles. You are given, let's say, 10 particles. So you can put 2 of them here, 3 of them here, 1 here, 5 here. So this is the problem. And each such level can have degeneracy. You know what degeneracy is? From hydrogen atom. That same n value but different angular momentum values, LMN, okay, can lead to same energy level. So those different L values or M values are like these cells G. This is real in case of quantum mechanics. In case of classical mechanics, it's kind of fake. We intentionally divide so because any energy is possible, right? There are no levels. So in classical mechanics, we divide them intentionally into these divisions. Like energy is continuous, but we measure them in a discrete way. Because after all, you will be using some instrument. You would have to take some range. And those ranges, like let's say 1 electron volt, 1.5 electron volt, 1.3 electron volt, like that. As you divide your bins when you plot, right, that graph paper box. So think of that like this. So you divide them in fake boxes. You can take very small box size or big. And those will be your boxes. And within that box, anyone can have the same energy. And then you can divide them into smaller cells. In any cell, the energy will be same.
but those are allowed cells, let's say. So this will be our thermodynamic system. We'll use this formula to derive Maxwell-Boltzmann statistics in the next class. Maxwell-Boltzmann distribution. I would like you to derive this on your own.